Okay, we're on lesson 10.3 on a few more tests to help us check and see if our series is going to converge or diverge. So the three tests we're going to talk about today are called integral test, basic comparison test, and limit comparison test, right? So what we're going to do from this point forward is just going to ask you a very simple question: whether or not this series is going to converge or diverge. You don't actually have to find the number that it converges to. You just need to answer whether or not it converges or diverges. So when you are asked to do so, you have to kind of prove to us why or how you know for sure this series converges or diverges. You can't just say, oh, the series diverges or the series converges, because it is, you could easily guess it and it's a 50-50% chance, right? So you have to actually tell us why you know this is true. Hence these tests. You can say, oh, blah, blah, blah converges because of basic comparison test, or this series diverges because of limit comparison test. So you have to give me the reasoning behind your claim of whether it converges or diverges, okay? So let's take a quick look. First things first, we're only going to deal with positive term series for now. We'll deal with negative terms later on. So rest assured right now it's all positive terms. Very nice. And then secondly, there's a really cool theorem here that just says that if your series is a positive term series and there's a number such that the sum of your numbers, as a summation, the series added up, is less than this m, then the series converges to a number that is smaller than this m. So basically, if your numbers are lining up below this number, like kind of like an asymptote, then your sum is going to converge to, less to that number as well. So kind of obvious thing, okay? All right, we have the first test. The first test is an integral test. So it says let a sub m be a series that is, you can replace it as a function, replace the n with the x to rewrite as a function, and then use our improper integrals to help us find the integration of the function and see if it converges. If it converges, it gives us a value, a number, then the series itself it converge as well. If the answer to my integral is infinity, then my series is going to be diverging. So it's kind of nice. So your integral is going to give you the answer of whether or not it converges or diverges with the answer to the integral. Okay. All right. So the first example here is we're looking at a series of 1 over n. Now, I know in the previous lesson, we talked about how this one is going to be a divergent series. So let's see why this is truly divergent, right? So start by setting it up as an improper integral 1 over x dx like so. And remind yourself of how this works. We set that up as t approaching the limit of infinity of my integral 1 to t, 1 over x dx. And then we're going to take the antiderivative like we normally do. So this is natural log of x, evaluate it 1 to t. Plug everything in, limit as t approaches infinity. Natural log of t minus natural log of 1, which is 0. So you get natural log of infinity, which makes this approach infinity. So hence, this is a divergent series, right? So because my integral here diverges, therefore, my series diverges. So therefore, 1 over n diverges by the integral test. So make sure you say why this is true. So this is true by the integral test. Okay. All right. Second one, I believe in the previous lesson, we also mentioned briefly that this is going to be a convergent series. And now we're going to see why this is truly convergent. Same setup. We're going to approach this as an improper integral, 1 to the infinity of 1 over x squared dx. Limit as t approaches infinity of 1 to t, x to negative 2 dx, right? So rewriting as a power allows me to take the antiderivative a little bit easier. So limit as t approaches infinity, we're going to start being more comfortable with figuring out this antiderivative. So x to negative 2 is x to negative 1 divided by negative 1. So negative 1 over x evaluated 1 to t, okay? Limit as t approaches infinity, this gives me negative 1 over t minus negative 1 over 1, so plus 1. So that's negative 1 over infinity plus 1. This will approach 0. So I actually get an answer of 1. So it's convergent, right? It converges to a number smaller than 1. So the limit gives us a convergent answer. Therefore, 1 over n squared is convergent by the integral test. So this is actually helpful, but most importantly, your series has to be integrable. That's a word. You should be able to integrate it. If you cannot take the antiderivative of it, then it is not a helpful test, right? Also, one thing to note here is that series itself has to be, the sequence itself has to be positive value, continuous, and most importantly, it has to be decreasing for every x on this. So in your homework, it asks you to prove that. You can simply prove the decreasing function by taking the first derivative and show that the first derivative is negative. Therefore, your function is continuously decreasing. You can also show continuity by making sure you don't have those issues in like rational functions, square root, even root functions, or natural log functions. All right. So hence, like all these I'm doing here, well, it's continuous on the positive from x greater than or equal to 1, right? So 1 over n squared, 1 over x squared. The only issue I have is 0, but since it's not in my domain, I don't have to worry about it. The rest of it is continuous. Okay. All right, last one here, we're going to still set it up as an improper integral. So it's going to go from 1 to infinity of x e to negative x squared dx. This one is a u sub problem. So we'll go ahead and set this up as limit as t approaches infinity, 1 to t x e to negative x squared dx. For me personally, I set the u sub up on the right-hand side or off to the side of my work. I actually work out the entire u sub and then put it back into my integral so that I don't have to deal with the u sub and all this notation, right? So off to the side, I set u as negative x squared. du is going to be negative 2x dx, and that would be negative 1/2 du is x dx. So my integral is really negative 1/2 e to the u du. When you take the antiderivative, negative 1/2 e to negative x squared, it will be my antiderivative. All right, so this becomes negative 1/2 e to the negative x squared, and then evaluated 1 to t, and don't forget your limit as well, it's still there, right? Okay, so plug everything in, limit as t approaches infinity, negative 1/2 e to negative t squared, minus negative 1/2, so plus 1/2 e to negative 1. Again, negative 1/2 e to negative infinity plus 1 over 2e. E to negative infinity will approach 0. So this integral gives me answer of 1 over 2e, hence making my series here convergent, right? So hence n e to negative n squared is convergent by the integral test. Okay, all right. A quick definition here is the definition of p-series. So what is a p-series? P-series is a series where you have a constant over n to the p power, right? So any series with a constant over n to any power, right? And then what's more important is the theorem. So this p-series will converge if your power is greater than 1, and will diverge if your power is 1 or less. So if it's anything less than or equal to 1, it will be divergent, right? So now we can use this idea to do a basic comparison test. We typically use these to compare to a p-series, or you compare it to a geometric series. So we're going to see both examples here. What is very cool here is that saying, and it's also very specific, is that if you have a convergent series to begin with, so here's kind of a graph, and you have a convergent series to begin with, so here's a convergent series b sub n. If I know that I have another series that is always smaller than that b sub n, that's my a sub n, you see how it's also converging, not necessarily to the same number, but it's also a convergent function. So if it's converging, you want the thing you're comparing to be smaller than what you know that is converging. So if I already know this series is converging, then I want another series that is smaller than that. So then I know that one is also converging. If that other series I'm comparing is bigger than a convergent series, then that doesn't tell me anything. So vice versa. If I know my series is divergent, so if my series is divergent, right? If I know that my series is divergent, so b sub n, then my other series that I'm comparing to has to be bigger than that to also be divergent. Because if it's smaller than that, it may not be divergent. It may be something else. We don't know. It just may have a different effect on it. Okay. All right. So now what we want to do is go ahead and use some comparison. So something that we start with is this. We take a look at our denominator. So I have a root n minus 1. So I ask myself this. Root n compared to root n minus 1. Well, root n minus 1 is going to be smaller, right? So root n is going to be bigger than that. Now, if I put a constant over those two terms there, right? So if you put a bigger number in the fraction, you'll get a smaller fraction. A small number in the fraction, you actually get a bigger fraction. So what was bigger before is now going to be smaller. So it's going to be this relationship here. Okay, that's useful. Now I remind myself that 3 over root n is really 3 over n to the 1/2. This is a p-series. In fact, this is a divergent p-series because p is less than 1, right? P is 1/2. So because that is a divergent p-series and your the function I'm comparing it to, this function here, is bigger than my divergent series, hence my series that I'm looking at is divergent. So then you can say, therefore, 3 over root n minus 1 is divergent by the basic comparison test. Okay, all right. Same idea in the next one. You have a 5 to the n versus 2 plus 5 to the n. Which one's bigger? Well, 2 plus 5 to the n is going to be bigger because I added 2 more numbers, right? I added 2 more. So now put it over a fraction. The bigger number now becomes smaller because it's a bigger denominator, right? So now I can see, okay, well, this function here is bigger than my other one. My original function, the series I'm looking at, is smaller than the one I'm comparing it to. So I'm looking for a convergent in the one I'm comparing it to because the one I am looking at, the one I want to know, is smaller. Smaller, convergent. Okay, so now I look at this series that I know, 1 over 5 to the n. Oops. 1 over 5 to the n is a geometric series. If you need to know, list out some terms and you'll see it's a geometric series with a ratio of 1/5. So this is a convergent geometric series, right? Your r is less than 1. Well, because I know that's convergent, and then the sequence I'm looking for is smaller than this one. So then, of course, therefore, 1 over 2 plus 5 to the n is convergent by the basic comparison test. Okay? All right. Last test that we're learning today is the limit comparison test. This one's very interesting because most of the time we're comparing these to p-series functions. So it's actually kind of nice, all right? So it says, let a sub n and b sub n to be positive term series if there is a real number such that when you take a limit, when you compare the two series of the series I know versus typically a p-series series there, if the limit approaches a number that is greater than 0, as long as it's greater than 0 and not infinity, then I know that either both of the series are convergent or both are divergent. So this is the one I don't know, but this one I usually do know. I will know that whether or not that one is divergent or convergent. And so if I'm able to get a number here, then whether this is divergent, then this will be divergent. If the one on the bottom is the one that you know is convergent, then this one is convergent. So they have the same exact behavior, okay? All right, so let's see the first one here. Here you have 1 over cube root of n squared plus 1. Reminding yourself of higher power rules. That plus 1 actually doesn't do much to my function, so you can really look at this as 1 over n to the 2/3. So what you really want to know is you really want to have another n to the 2/3 on top, so you have the same exact power, and then by higher power rule of rational functions, you can actually find a limit really nicely. So let's see how that works. So I'm going to take the limit as n approaches infinity of my original function, cube root of n squared plus 1, okay? And then you're going to divide that over by a p-series of 1 over n to the 2/3, right? Because first of all, that's how you're comparing. You're finding the comparison between these two functions as stated in the theorem here, where you go a sub n over b sub n. And now you're trying to see if this gives us a limit, right? So you want limit, oops, you're trying to do your algebra here, clean this up. Limit as n approaches infinity of 1 over cube root of n squared plus 1 times n to the 2/3 over 1. Okay, you can combine that into one fraction if it's easier for you to see, or you don't need to do this step if you already see what is happening here. What you want to see is then this n to the 2/3 over n to the 2/3, right? It doesn't matter what that one is, it's not going to do much for me. Since higher power rule says they're the same exact power, you just reduce them down, you get a nice 1. So is this number greater than 0? Yes, I have an answer. So because it is greater than 0, this is going to have the same behavior, top and bottom. So now I got to figure out what was the behavior of this, right? Because then if I know the behavior of that, then I can conclude the behavior of the function above, which is the series I'm looking for. So because 1 over n to the 2/3 is a divergent p-series, right? Because your power is less than 1, okay? So therefore, because I know that it's a divergent p-series, and since I had a limit to, I had an answer to my limit, so therefore the two functions will have the exact same behavior. Therefore, my original function of 1 over cube root of n squared plus 1 is also divergent by the limit comparison test. Okay, all right, try again. Next one. Again, higher power rule, let's take a quick look. We have the biggest power up here being 3 times 3n squared. The bottom is 2n cubed. So in order for these to be exactly the same power, I just need one more single n. So that will give me a nice big hint of what I am going to compare it with. So I'm going to go limit as n approaches infinity of 3n squared plus 5n all over 2n cubed plus 2n, right? And then you're going to compare that with 1 over n. It seems simple enough. And so now what you want to do is, okay, go ahead and clean up. Limit as n approaches infinity of 3n squared plus 5n over 2n cubed plus 2n. And yes, we know we multiply that by n over 1. So now the higher power becomes 3n cubed over 2n cubed. So the limit of this is 3 over 2. Again, I have a limit that's greater than 0. Perfect, I have an answer. That means they will have the same behavior. So what do I need to remind myself of? 1 over n is a divergent p-series. Right, so because that is divergent, therefore my original function will have the same behavior. 3n squared plus 5n over 2n cubed plus 2n is divergent by the limit comparison test. Sorry, I'm talking and writing at the same time, so it's getting really, really messy. Apologies. All right, last one. Again, we look at the higher power to kind of help us determine what is happening here. Highest power here is 8n. Highest power here is n to 7 over 2. So I know the difference between those two, and that's the n I'm looking for. The difference between those two is 5 over 2. Okay, so that means limit as n approaches infinity, 8n plus root n, all over 5 plus n squared plus n to the 7 over 2. I'm going to compare that with 1 over n to the 5 halves. Okay, all right, so now if I clean this up, limit as n approaches infinity, 8n plus root n all over 5 plus n squared plus n to the 7 halves times n to the 5 over 2 over 1, right, because you're multiplying by the reciprocal. You'll see your higher power will reduce you down to 8n to the 7 halves over n to the 7 halves. Your limit here is 8, and that is greater than 0. Perfect. That means then I have the same behavior. So then we look at this. 1 over n to the 5 halves is a convergent p-series because p is greater than 1. Okay, and so now you then can conclude that your original function of 8n plus root n all over 5 plus n squared plus n to 7 half is also convergent by the limit comparison test. Okay, all right, that's it for today.